Welcome to Topic 1, Lesson 9. In this video, we're going to talk about the molar volume of a gas. We're going to be able to describe Avogadro's law and how it directly relates gas volumes to moles, and we're also going to be able to solve gas stoichiometry problems. So the distance between gas particles is much larger than the actual volume of the particle itself. So let's look at the pictures below. We have two different gas particles. So we have a blue particles representing one gas, and we have red particles representing another gas. And what we're looking at is the distance between the particles. So the distance between them is much greater than the actual size they take up. So we could say that gas particles have negligible forces between them, and they pretty much have negligible volume. There's much more space between them than the actual size of the particle itself. Since the volume of the gas particles is negligible, Avogadro stated that equal volumes of gases, if they're at the same temperature and pressure, will contain the same number of particles. So it doesn't matter what the gas is, if it's at the same temperature and pressure, we have the same number of particles. So Avogadro's law is stating that volume is proportional to the number of moles. So we could set up this ratio. Volume over moles is equal to a constant. Volume is represented with V. K is a proportionality constant, and N is the number of moles. So volume is directly proportional to the number of moles of the gas at standard temperature and pressure, regardless of the gas. So you may remember this from 10th grade. We could, let's say, have a 2-liter container of nitrogen and another 2-liter container of oxygen. If they're both at standard temperature and pressure, we could say that they're going to have the same number of molecules. Recall the values for standard temperature and pressure. Standard temperature is 273 Kelvin, must be in Kelvin, and pressure is 100 kPa, 100. So the molar volume of a gas, which means that 1 mole of any gas at standard temperature and pressure, is equal to 22.7 decimeter cubed per mole. And that's the value that you're going to see more often, the decimeter cube value. So we know that whenever we're talking about STP, if we have 1 mole of a gas, we could use that value 22.7. So sometimes you might think in a question, how come they didn't give me the volume? But if they're telling you that it's at STP, just remember to keep that in the back of your mind for a gas. So example 1 is asking us to calculate the number of moles of chlorine gas in 45.5 decimeter cubed at STP. So we see that we're talking about a gas, and we see that we're at STP. So we know that we could use the value of 22.7 decimeter cubed. You start with your given, which is 45.5 decimeter cubed, and we convert to moles, and we see that we have 2 moles of chlorine gas. In our next example, we're being asked to calculate the volume in centimeter cubed occupied by 3.20 grams of carbon dioxide at STP. So first, we're taking our grams and we're going to moles using our gram mole calculation, and we have 0.0727 moles of carbon dioxide. Once we get the moles of carbon dioxide, we're going to convert into a volume. So we're going to multiply by 22.7 decimeter cubed to get 1.65 decimeter cubed. We're using this value of 22.7 because we know that we are at STP and we're talking about a gas. So this is the molar volume. So 1 mole of any gas has a volume of 22.7 decimeter cubed. Once we get our decimeter cube value, we're going to use our conversion factor to convert into centimeter cubed because the question asked for the volume in centimeter cubed. And if you forgot this ratio of 1 decimeter cubed per 1,000 centimeter cubed, this is in your data booklet. In our next example, we're looking at what volume of hydrogen gas is produced when 0.6 moles of magnesium reacts with excess acid STP. So what we want to do first is write out a balanced equation. So we take our magnesium, we're reacting it with hydrochloric acid, and we form magnesium chloride and hydrogen gas. We start with our moles of magnesium. We do a mole ratio to try to figure out how much hydrogen would be produced here. So we have 1 mole of hydrogen, because our coefficient is 1. We have 1 mole of magnesium, so we get 0.6 moles of hydrogen. And then what we're going to do is try to figure out what the volume of hydrogen is. So since we're again talking about a gas at STP, we could use the 22.7 value. So we take our moles and we can multiply it by 22.7 decimeter cubed per mole, and we get 1.36 decimeter cubed. Okay, so here's our last example. We're going to step it up a little bit. We're going to do a gas calculation involving limiting reagent. So at STP, 30 centimeter cubes of ethane reacts with 60 centimeter cubed of oxygen. Which one is present in excess? How much remains after the reaction? What volume of CO2 is produced? So first, we got to figure out which one's the limiting reagent. So what we do is we take our C2H6 here, our ethane. We have 30 centimeter cubed. What we're going to do is do a mole ratio to figure out, we have 4 CO2 here, we have 2 ethane here. Same thing for oxygen. We have 4 CO2s and now we have 10 oxygen, so we're looking at the mole ratio. And we figure out that since less oxygen is produced, oxygen is going to be the limiting reagent. So that means that ethane is going to be the one that's in excess. Recall that for volume problems, where we're looking at how much is produced, since we're given the value initially as centimeter cubed, we're not going to go to moles and then back to doing a mole ratio and then back to volume. For volume, it's sufficient just to do a mole ratio to figure out which one is the limiting reagent. So now that we know that ethane is in excess, we want to be able to figure out how much excess is left over at the end of the reaction. So what we'll do is we have 60 centimeter cubed that we were given, and we want to subtract out how much we actually used to figure out what volume is going to be left over. So what we do is we take the 60 grams that was actually used of oxygen and we do a mole ratio, so you have 2 moles of ethane and 10 moles of oxygen to figure out how much was actually used of ethane, and that's how we got the value of 12 here. So in this video, what you were supposed to understand is what the molar volume of a gas is. It's given in data booklet 2, and it's a value that's a constant, 22.7, at a specified temperature and pressure. We should know that Avogadro's law enables us to use the mole ratio of reacting gases to determine the volume of gases, and we want to be able to calculate any problems that are going to use volumes of gases using Avogadro's law.